Oh, this is fantastic. Well, Bob, it is such an incredible pleasure to be able to spend time with you today on the 40th anniversary of the first Ethernet specification. You're the father of the Ethernet. You're the inventor of the Ethernet. Of course, as always, we have lots and lots of collaborators, but your contribution to the foundation of the internet today its impact can't possibly be overstated. You've had an amazing career. You were born in 1946. Your career really started then. You were born in 1946, which is also the birth date or the birth year of the transistor. The two of you enabled the internet that we know today. And now you went on to an incredibly celebrated career. You're a recipient of awards that are countless. The National Medal of Technology, the IEEE Medal of Honor, the Internet Hall of Fame, the Alexander Graham Bell Medal, the Grace Murray Hopper Award. The Computer Science Awards can't possibly recognize fully the contribution you've made to the world and to society today. You know very well that the invention of the Ethernet is what enabled the internet today, where billions of people are connected to it. Trillions of dollars of the economy is enabled by it. And because of the internet, it is possible for us to be in the same, although not in the same physical space, to be able to enjoy each other's presence in the same digital space. And because of the internet, it's possible for companies to become global companies, to be a virtual giant companies with sites in Silicon Valley and China and India and European sites all over the world to form today's great companies. When you go back and think about the beginning of it, what inspired you? Of course, everybody knows what Ethernet is. Everybody knows the essential technology of it, the amazing breakthrough it's enabled since. But the things that I want to talk to you today are really the inspirations behind it. What was the inspiration behind the invention of Ethernet? What was the problem you were trying to solve? And what were the surrounding conditions, the surrounding environments at Park that inspired you to invent Ethernet?
Well, thank you for those many kind words, Jensen. I'm honored to be with you here today. And I got into the networking business in 1969 because I showed up at Harvard as a grad student. And the algorithm that grad students follow is they find out where the money is, and then they decide to major in that. So the Advanced Research Projects Agency of the Department of Defense was giving out money to computer science departments. I detected that, and so I became an ARPANET grad student. And at MIT, as a student at Harvard, but as an employee of MIT, I connected MIT to the ARPANET, the then internet, and I learned in the course of that how to send bits one at a time down a very long wire. Then moved to Xerox Corporation, Palo Alto, Xerox PARC, where I put PARC on the ARPANET. I just did the same thing, built the same hardware.
Now, when you put Park on the ARPANET, it must have been one computer. When you say Park, I mean, was
Yes.
it one computer at Park that you put on the ARPANET, or was it Park that you put on the ARPANET?
It was one computer. Name was Max, M-A-X-C. It was a PDP-10 clone that we built in that lab. And I was the networking guy in the computer science lab there, so I got the job of connecting it to the ARPANET. Basically building a printed circuit card about this big that would connect the time-sharing system, the PDP-10, running the 10x time-sharing system, connecting it to the packet switch, the ARPANET packet switch in the same room. So once again, sending bits one at a time down a long wire.
So you were a system designer as well as the network administrator, so to speak.
I operated at the boundary of hardware and software. So I would build hardware, I would write software at the very,
And this,
but just the plumbing level. And my whole career has been at the plumbing level.
well, you're the world's most famous plumber. There's no doubt. You and Mario both. Now this printed circuit board that you made is made out of what kind of technology at the time? Is this TTL, MSI type technology?
Well, actually, I just lied. I didn't make a printed circuit card. I made a wire wrapped,
Uh-huh.
a big wire wrapped card, and using the Texas Instruments 7400 series MSI chips.
Oh, fantastic.
You remember that? That was a
Oh
chip.
yeah, of course.
What was it? The 7404 had two flip-flops on it, and the what was it? The 7400 had 6 inverters. And anyway, getting the chips on the card was part of the limiting factor. So let me move on to the Ethernet, because after we put Xerox on the ARPANET, we then decided to put a personal computer on every desk. And I lucked out. They gave me the job of connecting them together.
But Bob, at this time, the PC hasn't been invented yet. You were at Park, and so with the personal computer, was it called a personal computer? It was probably Alto that you're talking about.
Was the Alto. We did call it a personal computer.
No
By the way,
kidding. Uh-huh.
you could get into a big argument about, one could, which was the first personal computer. But the Alto at Xerox Research is my version of the first personal computer, and
Sure.
I lucked out.
Yeah.
I got to build a network. And one of the requirements was that we were also building the world's first laser printer. Page per second, 500 dots per inch. If you do the math, 500 times 500 times 8.5 times 11 per second, it's about 20 megabits per second. So the network had to be fast. We couldn't use RS-232, which was the then standard. So in my office, the day before Ethernet, I had a 300 baud dumb terminal, and then when we installed Ethernet in my office, I had a 2.94 megabit per second packet switch LAN in my office.
Megabit per second. Whopping numbers. But
Just
they
to
were
save you
whopping
the
numbers.
arithmetic, the increase was a factor of 10,000.
Wow. Well, it took us another 40 years to do much better than that, but not much better than that.
Oh, no, we're
that was
doing.
a huge leap.
There is a group doing 800 gigabits per second Ethernet right now,
Yeah, right. And so
and
every
that's
gigabit per second, that's 100,000 times about, right?
47,000 times, but who's counting?
Yeah, well, good. And so my first experience though with Ethernet was it was a local area network it was called a LAN, and it was really about connecting computers that were close by. And my first use of it was really connecting peripherals. Now the from that point in time, to the time we are today, where Ethernet is clearly not just about peripherals, it's not just about local area networks, it's not even about coax and twisted pairs, it's so much more than that. The first step of that, of course, was the standardization of the technology that you invented, and that standardization process. What was happening at the time? What inspired you to go to IEEE and made it eventually to 802.3?
So I left Xerox in January of 1979 with the intent of starting a company, although I had no clue what it would be. And in a meeting in February of that year with Gordon Bell, who was then the vice president of R&D of Digital Equipment Corporation, the #2 computer company in the world.
Yeah, I know Gordon. I know Gordon very well.
So Gordon asked me to design an Ethernet for DEC. And I said, I couldn't do that, Gordon. First of all, I feel loyal to Xerox. And second of all, I've already designed the best network I know how, and yours would be second best. So together we had the idea of writing a letter to Xerox proposing that DEC and Xerox would work together to get their products to be compatible over Ethernet. And then I ran into Intel Corporation down at the National Bureau of Standards looking for a new chip standard to implement with some new NMOS thing they had. So pretty soon we had DEC, Intel, and Xerox cooperating on connecting with Ethernet, and suddenly they had a problem. They couldn't meet because in order to meet, they would have to violate antitrust law. So I got my lawyer, a fraternity brother I might add, Howie Charney, and he gave me advice what I should tell the lawyers at those three companies that would make it okay for them to meet. I gave him that list of 5. Wanted no marketing people allowed in the meeting, no pricing discussions, and the goal had to be an industry standard. So that was the moment in which the idea of creating an industry standard Ethernet came up. And you have to remember, in those days, standards were not made like they are today. I mean, IBM would just announce its next product, and that would be a standard right away.
That's
so
right.
The idea of bringing Ethernet to the IEEE was an important breakthrough idea.
Now, Bob, at this time in your life, how old were you? You started 3Com. How old were you?
I was 33
Must have been about 30.
33.
33.
Yep.
Incredible. Well, at that time, there weren't that many technology startups, quite frankly, and surely at 33, that's quite young. And who did you work with at Intel? You know, for gossip's sake, who was CEO at the time?
Andy Grove was the principal mover, but a guy named Kaufman, forgotten his name, he was Grove's right-hand man, and he came to a conference pitch I gave on Ethernet, and then he invited me back to Intel to give a presentation at Intel, and I met Mr. Grove, and they were instrumental in getting Ethernet standardized.
That's really quite amazing. Now, at the time, there were a couple of other competing standards that were being proposed. Token ring and token bus was being floated around. You know, how did you guys decide? How did the community decide that the standard would become Ethernet? You know, were there technical merits? Were there economic merits? Were there industrial support merits?
So on September 30th, 1980, the event we're celebrating today, DEC, Intel, and Xerox produced a spec, the Ethernet Blue Book it was called, and gave it to the newly forming committee IEEE 802 with no dots, just 802. And we thought that Project 802 would then standardize officially Ethernet. But IBM and General Motors had two different ideas. They didn't like the idea of somebody else making standards for them, so they each submitted a competing proposal. IBM's token ring and General Motors token bus. And the IEEE then began to consider the three of them, and eventually, I didn't like this outcome, but eventually standardized all three. And that's where the dots come from. 802.3 was Ethernet, 802.4 was the token bus, and 802.5 was the IBM token ring. And the way we proceeded from there was fierce competition for the next 20 years.
Now, if I were a startup at that time and it went through the standards bodies and IBM's was 802.5, I might be inspired to go build that, frankly. What were the conditions that caused Ethernet to have gained so much industry support? I know that one of the things you always believed in was interoperability and compatibility, and of course for any platform, for any standard, that is the essential core value that allows an industry to be formed around it. But at that point, IBM had put out token ring to be standardized, and why wouldn't anybody want to build peripherals or computers that would be connected to the world's leading computing company at that time? You know, what caused?
IBM wasn't used to fighting standards efforts like Ethernet. And their heart really wasn't in it. Their dark black heart was intent on pretending to have a standard, but shipping a product that was not standard. And the way I know this is that 3Com, my company, we shipped IBM Token Ring ahead of IBM. And we had a hell of a time selling it. We never sold very much of it because IBM, whose heart was not in interoperability, had software dust. that they sprinkled over their token rings. And so whenever we tried to sell a token ring into a customer, we couldn't get it to work because they had this.
Oh dear.
This software dust was called, they called it SNA, System Network Architecture.
Oh,
Just to annoy them, I used to call it SNA.
Well, if you added technology to it, it would be called snot.
God, I hadn't thought of that after all these years. But going back to your question, the reason that people uh, went to Ethernet eventually is that number one, Ethernet was designed in the context of the 7-layer reference model of the Internet. And so we knew our place. And so the Ethernet was designed to be level 1 and level 2 and not the other levels. And IBM didn't understand this, and nor did General Motors. So for example, Ethernet does not have acknowledgments. You send packets. The packets may or may not be acknowledgments, but Ethernet doesn't know. They're just packets. So the whole idea of acknowledging things was, we assumed would happen at a higher level with TCP, basically. Whereas IBM felt out, because they were a bit old-fashioned, felt obligated to have acknowledgments, namely that token in their ring would go around acknowledging that the packet that you sent has gotten there. And that was built in level 1 and 2, and that was a mistake.
Yeah.
So IBM Token Ring was always slower and more expensive than Ethernet. So that was another feature.
Yeah, and the wisdom of specifying Ethernet was to go as far up as possible, to specify as much as necessary, but not more than that, so that you can enable innovation and evolution on top.
Right.
Yeah, that was really great wisdom. And so now 3Com was founded, Ethernet was standardized. You're competing against IBM. Who was 3Com's first customers? Who are the people that got you off the ground?
Well, there were a lot of people over a long time got us off the ground. I think the Ethernet bandwagon was joined principally by Hewlett Packard and DEC, Intel, Xerox, and 18, 19 other companies. So it was all of us versus IBM and a few of its close friends. And the hard part is that there weren't any PCs, and the whole purpose of Ethernet was to network PCs, and there weren't any. I mean, there were 100,000 maybe Apple IIs floating around. But the Apple II was an 8-bit 6502 microprocessor, and it wasn't worthy of a 10 megabit per second Ethernet. So we had to wait, and we had to wait for the IBM PC to come out it was announced in August of '81. And then we built a card that we shipped in September of '82 that you could plug into an IBM personal computer and put it on the Ethernet. And then it got difficult because people would say, well, what good is Ethernet? And I would say it's good for everything. It's great. It's a horizontal platform. It's not a vertical or anything. And it turns out that is not a good value proposition. So if anybody's planning to say they're selling a platform that's good for anything, customers don't respond to it.
Yeah, right.
They want to know what it's going to do for them.
Yeah, right, exactly.
So would you like to know how we sold the first Ethernets?
Well, I think this is such a great story, and Bob, this is really your second invention. The first invention was the technology, and your second invention, and arguably even a more insightful invention, because the question that I will lead to next, I'm going to tell you what my next question is, and I'm interested in hearing your thoughts on this. Is what is Ethernet? Because Ethernet could be many things. It's a technology, it's a standard. Of course, it's networking is a market. It's the fabric of the market, the nature of the market, the people in it, the competition of it, and then is it a platform? And I think in a lot of ways it's all of that. And your insights, and it's so funny the first time I heard it. Your insights, and I'm going to let you tell it, but your insights and you were at the time in sales and marketing. You were probably the most educated sales and marketing person in Silicon Valley at the time, and because you were trying to evangelize a brand new a new way of thinking about computing. Uh, uh, in fact, that intersection between your background and your ability to think about customers and creating markets came together at that time. But it was your selling to a customer that I thought was fantastic. Now, tell the story of how it came about.
Ah, well, I have 50 stories that meet that description, but I
Now
was,
this is your the value of a network is proportional to or equal
oh,
to
right. All right,
the
so we're
square of the
selling
number of
Ethernet
connections.
to people with personal computers, of whom there aren't any. So we had to make it easy to try our product. So we made a trial kit, a 3-node kit, 3 cards, option cards, and a diskette with software on it. And this cost $3,000. And what you could do with it is you could share a printer among the 3 PCs, share a disk among the 3 PCs, send emails among the 3 PCs, etc. And we sold a bunch of these, and it was only $3,000, so people were curious, and they bought it. And then they all came back and they said, uh, "Works just like you said it would. We can share the printers, we can share the disks, blah blah blah." And by the way, sending email among 3 people isn't that interesting. Your product isn't useful to us. And I was then, as you pointed out, the head of sales and marketing, so that was my problem. So one night I went over to Stanford, and we Xerox had given Stanford some Altos. So I snuck in and used the Alto, which I knew how to use, and I made a slide, a 35 millimeter, not a PowerPoint, a 35 millimeter slide that showed that the cost of a network, about $1,000 a card, was a linear with the number of nodes that you had in your network. But the number of possible connections, which I claimed was the value of the network, grew as the square, because every node you added could talk to the preceding n-1 node. So n times n-1 is roughly n squared connections. So I argued that the value of a network grew as the square, and therefore would eventually overtake the linear. That's some critical point. By the way, I made 6 copies of this slide because that's how big the sales force was. 6 people. And the slide basically said your network is not useful because it's not big enough, and the remedy for that is to buy more of our products. And they believed us.
Now, who was the
And
first customer that believed you?
oh,
What was your first large
I
installation that was more
remember.
than one card?
Well, I remember a young man in Maryland who worked for a bank, and he was going to build a small work group of PCs connected by Ethernet with a multi-user accounting package. And he may have been an early customer. By the way, I learned a lesson from him. I learned why people buy products from startups. Why would you take the risk of buying a product from a startup? Why would you do that? And he explained it to me. He says, "I want to be the president of this bank. And this work group that we're building here, this work group multi-user PC network, is going to save us a lot of money and make me look good, and I'm going to get promoted and move up." So the reason people buy,
Yeah,
the cutting edge technology is because they have competition and they want to
yeah,
win, and
yeah.
we help them
Saving
win.
money and saving time. Saving money, saving time.
Yep.
Yeah, that's really fantastic. It's such a great story, and of course, you started the company before the PC revolution really started, and so you must have written a business plan that excluded the PC revolution. Did you see it coming, or how did you scope out the market? Because the market was everything that was left over from IBM, which wasn't much. I mean,
Not
DEC was very
much.
successful, and I don't think Sun wasn't here yet, and so what was the market you were addressing, and how did you
Well,
write
I
out a
had a
business
business
plan?
plan. It was spiral bound. It was on brown paper, and it was available on its first draft on September 30th, 1980, the same day as the Ethernet Blue Book, because my plans were predicated on the issuance of the Blue Book, and that the specs would be adequate to build a company, and they were. So I then began showing this business plan to people, and their first complaint was, there's no market research in your business plan. And my answer was,
Uh-huh.
this company that I'm proposing is market research. If there's a market out there, we'll find it, and if there isn't a market, we'll go under.
Gosh, I wish I had that line. Well, this is that
I
line
had
is
that line.
that sounds a little bit that line sounds a little bit like if you build it, they will come.
And I'm glad you came up with that phrase, because in answer to the question, what is Ethernet? One of the principles of Ethernet is build it and they will come. That is, when we built that first Ethernet to run at 2.94 megabits per second, we did not have a requirements document from anybody saying they needed 2.94 megabits per second. We just built it as fast as the semiconductors would allow. And that's been a principle of Ethernet. They're building an 800 gigabit per second Ethernet right now.
Yeah,
I'm certain there's no one requiring it,
that's right.
but build it and they will come has worked for the last 40 or 50 years. So I think, yes, build it and they will come.
Yeah, and I still remember when we started the company, somebody said that to me too. It's like, if you build it, so what you're saying, Jensen, is that if you build it, they will come. And my response to it was, if we don't build it, they can't come. And so all innovators that are out there taking a chance and they believe in something, they have to build it based on dreams and hopes and confidence that there's a world of innovation out there, that so long as the platform could reach millions of people or millions of developers and smart people, somebody's going to build something amazing at some point. Now, we go back and most people think of Ethernet. If I said Ethernet, most people will think of it as the networking technology. Of course, that networking technology is interoperable because it's a standard. The technology, as you know well, it has evolved tremendously since the beginning, since your 7400s and the MSIs and the specification of Manchester encoding and the foundational layers of the physical layer, the data layer. The technology itself has evolved tremendously, and one of the things that you said earlier, which, as far as semiconductor technology could enable it, in the case of Ethernet and switching technology, it's engineers are pushing the boundaries beyond semiconductor physics, in fact, Shannon's law was thrown at you in the early days where you were developing and seeing the evolution of Ethernet that had gone beyond Shannon's law. Tell me about that moment. How did you react to it? What was, did you think that there was a physical limit that was very, very close?
Well,
Did that
well,
concern you?
well, if you thought having IBM and General Motors attacking you, wait till AT&T attacks you. And AT&T
Attacks you with a
attacked.
law, with a physical law,
They attacked
information
us.
law.
Yep, with Shannon.
Yeah, right.
The Bell Labs geniuses, and many of them were geniuses, said that the copper that had been put in by the telephone company for over 100 years, connecting all those telephones, had a Shannon limit of 14.4 kilobits per second. And so all this talk about megabits per second wasn't going to work over this pitiful copper because of Shannon's law. And then one day someone started selling a 50 kilobit per second modem to run over the AT&T copper, and it worked. It worked just fine. I remember going to conferences, rubbing AT&T's nose in that. I said, "What about this Shannon limit thing
Yeah,
that you guys
yeah.
have?"
Well, you remember FDDI versus CDDI, that we had reached the limits of copper and we had to go to fiber, and fiber was really expensive at the time, and so the idea of 100 megabits per second was going to be too difficult to reach. It was too expensive, and that company, the startup company that Cisco ultimately bought, came up with 100 megabits over copper, and unleashed another, several orders of magnitude innovation after that.
That was Grand Junction Networks, and
That's right, Grand
I
Junction.
helped found
Yeah,
that company with
yeah,
my
that's right.
partner Howie Charney. But I have a theory about your company, which I'd love to test on you right now. And my theory is,
No,
you
no, no,
sell.
no. This is not about me, Bob. This is about
No,
you. Give
well,
me a second.
it'll
This is my
it'll
time.
get
You
back
know,
to me.
hundreds of thousands of people, millions of engineers are going to watch this. They came to watch you, and so let me get something out first. So you and I we've built companies, and we've done a lot of things. We failed at a lot of things, and failures are great teachers, and we learned a lot from failures. Uh, Failures are great teachers, partly because of the emotional angst, the surprise, the disappointment that forces you to reevaluate, to be introspective, and to do deep analysis to understand what happened. And as engineers, we'll always go back to first principles and recreate the model that predicted the first outcome, and refine that model so that we could predict future outcomes. And uh, so failure is a great teacher, and I wouldn't mind hearing about some of the failures. However, the thing that's really extraordinary also is when something is a spectacular success, it's also an excellent teacher. I've found also that when you look at something that is an extraordinary and spectacular success, to be mindful of analyzing what were the dynamics and the events, or their circumstances that caused the extraordinary success. Some amount of serendipity helps, some amount of accidents help, but not really. And what were some of the lessons that you took that enabled Ethernet to be the magnificent success that it has become, the fabric that has connected the planet, that all of computing is built on today? What did you take away from that? What were some of the learnings that you would repeat when you start another company, or that you would advise the young entrepreneurs that you're advising these days?
You almost said this, but let me say it. I think you learn more from success than from failure, because there are so many more ways to fail than there are ways to succeed. So if you find a way to succeed, you have found something of great value. And you remember now, Ethernet was a 1973 invention, so it's gone through a lot, and the technologies have evolved, and almost every mistake you could make has been made. Let me try to recall a few. In the building of 3Com, one of the mistakes we made a few times was to focus on our competitor instead of our customer. So we went against Novell that made PC networking software. We spun our wheels for 2, 3, 4 years fighting Novell. It was a complete waste of time. And then later, the year we went public, a startup started called Cisco, and we didn't give them enough respect. We didn't pay attention to Cisco. Now, it took them a long time, but they eventually blew past us out in the 90s or so. And the mistake we made there was that they introduced routers with 14 protocols, and we had routers with 2 or 3 protocols. And being standards experts, we figured that you only needed 3. But Cisco went out there and offered 14, and guess what? The customers wanted 14 protocols because they were filled with uncertainty about the future
That's
of the
right.
network.
They wanted
And
14 because they're not sure exactly how many they
yeah,
wanted.
they
Yeah,
wanted to future-proof
yeah,
their
right.
acquisition, so they wanted to be sure that no matter what protocol won, they would have it. So that's how Cisco slipped by us in the early fights over who would sell routers. So that's a lesson. Um, are you going to let me propose what I think about your company?
Okay, fire away.
Well, it'll
there,
get back to
there
me
are
soon.
so many entrepreneurs on this that would love to hear from you, uh, the lessons that you've learned. You've dedicated the last decade of your career investing in companies, creating frameworks for innovation, for entrepreneurs to think about the starting of their company. I'm personally dying to hear about it, and I know that there are millions of young entrepreneurs who would like to hear about it as well. And so long as we can get back to that, I'll answer any questions you have.
Well, my theory of NVIDIA is that I go beyond the GPU. So clearly NVIDIA is the GPU company, but I don't think that's your secret. Your
Mm-hmm.
secret isn't the GPU per se, it's the interconnectivity among the GPUs that's your secret weapon. So you're in the same business I was in, connecting things together. I was in the business of connecting PCs and mini computers together. You're in the business of connecting GPUs together. What do you think of that theory of your company?
Yeah, the connectivity of small processors that are orchestrated and scheduled, you know, micro scheduling of a large network of processors, and it's very difficult to take um, uh, uh, very complex programs to have it be distributed across all of these processors, have them be coordinated to communicate their intermediate results, and then to get everybody going again. That orchestration, that scheduling, is a very complex problem. I mean, it's the supercomputing problem. It's the large scale, massively parallel problem, and so the technology is complicated from that perspective. Uh, People think that on-chip networks must be easier to do, and it is easier to do than the internet, of course. But the speed at which we communicate with thousands of processors, all able to talk to each other simultaneously, this fabric that we call it inside the chip, our internet, if you will, is enormously complicated. It's a machine in itself. Um, uh, Tens of clock cycles are propagating across the fabric from thousands of processors all at the same time, and we have to keep the latency down, the throughput high, and it has to be resilient to very large ranges of functional temperature and operating temperature and process skews, and we're trying to keep everything down into the nanosecond, and so the bit rate is really high. I mean, it's a technology miracle, and so that part of it is the giant breakthrough of a GPU, if you will. The breakthrough but that's the technology. And as something you said earlier, customers don't care about your technology; they care about their problem. And I would say that the wisdom of our company was to recognize that a GPU is a component like a DRAM, like a CPU, like a network processor, and so it's a technology component. How we formulate the entire solution to serve large domains of problems is really the breakthrough from a business perspective. And it was a very challenging business model. And the way we articulated it was, look, there's all these microprocessors, they're moving at the speed of light, or they're moving at the speed of Moore's law. Everything we build next to it gets sucked into it. Everything we get built next to it got sucked into it. And um, and I still remember our company was teed up as a business case that was in the early days. And I wish I have the presentation now, but it was presented to a visiting professor, Andy Grove. And at the end of the business competition, we were described as a company that had no hope and would likely go out of business very soon. And the reason for that was a very good one. First of all, uh, the articulated strategy of our company was to go solve challenging problems that are very large and sustainable, has great impact in the world if solved, but that are not solvable by ordinary computers, otherwise code for CPUs. And so if you're choosing a problem that's not solvable by CPUs, either that market doesn't exist because the solution doesn't exist, or that market is extremely small and it's a supercomputer market. And neither of those conditions leads very well to a successful startup or a sustainable company. And so that was the articulated mission of our company. This is the problem we're going to go solve. The second problem is you sit next to the single largest, the single most powerful black hole of technology in the history of humanity, that everything near it gets sucked in. And you could be traveling at the speed of light and still only be stationary next to it. And so the ability for a startup company to achieve R&D scale and not be sucked into the CPU because of Moore's law was probably close to impossible. So between those two impossible conditions, Andy assessed that this company, though interesting, is not likely to succeed. And I would say that the assessment was not wrong. There was one piece of one observation or one insight, and as you know, these market insights or strategy insights or innovation insights make a tremendous difference in how technology companies are ultimately formed. And the insight that we had was that the PC was coming. And it's not likely that the most important killer app is recipes. It's not likely that the killer app is spreadsheets. It's important for office automation, but it's not likely to be the technology, the application that puts a PC in everybody's, if you will, everybody's homes. And we of course, we came from the workstation industry, the semiconductor industry, so we know very well what workstations can do, and they were all connected by Ethernet, and the killer app was a flight simulator where we're chasing each other around the Bay Area, and we're all sitting around just laughing, chasing each other, having a great time because we're suspended in this virtual reality world, networked together. And so we theorized that someday the single largest consumer application is going to be virtual reality, video games, 3D games, and that everybody's going to be a gamer. Who wouldn't want to be a gamer? And this platform that we're going to create would enable this new industry, which at the time I think Electronic Arts had like 12 employees. The 3D graphics video game market was completely non-existent. There were no standards. DirectX didn't exist. OpenGL didn't exist at the time. And the PC had no sound. The PC had very poor graphics. The PC didn't even have joystick ports that allows you to interact with games. And so we imagined that someday the PC would evolve into this thing. If we created this, if you will, accelerated computing device that would enable these applications, and the first application would be a video game, it could be the economic engine that gets the flywheel going. That because this industry, video games, who wouldn't want to play it? And the technology was so hard, the technology complexity times the size of the market would drive our R&D. Well, that insight, that equation has proven to be true. And this device that sits next to the CPU, the microprocessor, that accelerates domains of applications that we have to go figure out, and we have to go evangelize, that we have to create the software stacks for. This approach to creating markets has proven to be quite a good one. And now, as Moore's law has ended, we found ourselves in a time where this new era is coming along called AI. Computer science has found a new way of writing software, and this new way of writing software is a very specialized domain that requires tremendous acceleration that microprocessors can't do. we found ourselves in the right place at the right time with the right set of skills, the right scale, the right perspective on how to invent and create new markets and new computing stacks. And so I think it's part insight, part technology differentiation, part strategy, part serendipity.
I never went to one, but I've heard of things called LAN parties, local area network parties. So
That's right.
apparently
Yeah,
they were playing video
that's where
games.
your work and my work came together.
Yeah. Now I know what they were doing.
Bob, it's really quite remarkable. The video game industry not only has it become the largest entertainment industry in the world, it's also used as a form of art. The graphics are now so beautiful you could mishmash them together to tell news stories. People use it. People use it. Esports. It's one of the fastest growing sports. Uh, the people who play esports have incredible reflexes and snap of a finger thinking and strategizing in real time. It's like playing real time multi-dimensional chess, and they're incredibly good at it. And now we're seeing real sports coming into esports. And so this is F1 racing, NASCAR. The actual pro racers are sitting in these networked, Ethernet worked pods that are racing each other, and they say it's as intense as driving the real thing. And so video games sitting on the fabric that you invented makes it possible for us to network all of these gamers together. It absolutely follows Metcalfe's law, and Metcalfe's law has made all of these social games, uh, massive online multiplayer games, which is built on a network. It is the reason why the video game industry is so large today. It is
So,
absolutely based on network laws.
so today we're celebrating the standard, the first spec, the Ethernet Blue Book, September 1980. And I argue that the standardization of Ethernet explains its success. That is, by making it standard so multiple people could invest in it and multiple people could interconnect with it. I'm wondering, is there now a standard that needs to be made or two standards or three in gaming to advance gaming? Are there standards issues in the
No,
in the
that's I think you got it right. The standards makes it possible for horizontal, what is described typically as competition, but it's really horizontal co-opetition. That between a lot of different players, you're able to create a total solution for the marketplace that no single company can. On the other hand, the standard of Ethernet was sufficiently high level that it could be a foundation by which, but not so high level, that innovation on top could happen. And so therefore the internet was built on top of it. And because the internet was built on top of it, now that's a platform by which all kinds of applications are built on top of. And so the brilliance of Ethernet, the standard, is that it's really, to me, a platform, the ultimate platform strategy, the ultimate platform innovation, and sufficiently specified, but sufficiently open-ended. That fine balance is what makes it possible for this rich ecosystem to have developed. And I think it's completely genius. Like poetry, it's completely genius to figure out exactly what the words are and where to stop it. And that genius, I think has enabled all of these industries to happen. Now, the video game industry, we have specifications like DirectX and OpenGL, and those industry standards has absolutely enabled the video game industry to flourish. Now, one of the things that, Bob, that I want to talk to you about now is what's next. The thing that's really exciting, and we started the conversation, and it's about the announcement of ARM and my interest in it, and the reason why I think it's going to be so important for the next era of internet. And the basis of my theory is this: that the internet is today used largely by humans that are interacting with information and enjoying content and connecting with each other. It's largely, it's value, the n squared value. The n is humans, largely humans. And, uh, and it's created trillions of dollars of economic value. And of course, accumulated over time, trillions of dollars of economic value. And the thing that I'm excited about is the confluence of a few technologies that we've been working on. One particularly that's going to activate a new internet. Now, of course, it's an overlay; it's a connection to this internet, but it's really a new internet, if you will, a new internet of autonomous machines. And these autonomous machines are going to be interacting with the internet. They're going to be interacting with each other, and because of AI, you could write software for the very first time. And uh, computers is just a box unless there's software. And for the very first time, we could write meaningful software that activates these computers at the edge to do interesting things and otherwise seemingly intelligent things, like drive cars, do agriculture, keep cities and streets safe, and move trucks around, and robotic arms and things like that. And that internet, unlike the current one we're in, is not sporadic in the sense that we use the internet today sporadically, and in the context of nanoseconds. We interact with a computer once every infinity practically, but in the future, these machines are going to be interacting with the internet and interacting with each other continuously. The size of the next internet we're going to build is thousands of times bigger than the current internet we enjoy. And so that's the reason why we bought ARM is number one, we love their business model. Their business model makes it possible for companies far and wide, whether they're in industrial equipment or manufacturing equipment or automotive or whatever it is, consumer electronics or whatever it is, for them to be able to build computers. And what we like to do is to add to this network that ARM has with AI computing technology that we're very good at, to offer it to the ARM ecosystem so that they could build interesting computers using the same business model. And by doing so, we'll be able to automate, bring AI, make possible these autonomous machines to be intelligent and connect to the internet in a meaningful way. And so we bought ARM for that reason, so that we could accelerate, if you will. We could bring AI, if you will, AI computing to the ARM ecosystem. And so that's the journey really laid on the foundation that you laid. We would like to enable the next generation, the next chapter of the internet. And so, what do you think about that?
Would you call that the Internet of Things?
Yeah, absolutely. It's the Internet of Things. And I would say, Bob, that the Internet of Things has been floating in tech for practically a decade now, but we've just not been able to activate it. We've not been able to turn it on per se. And the reason for that is because the things need software, and the things oftentimes can't be connected to the cloud. And the reason for that is because they're too chatty. They're just talking continuously, and you can't put the autonomous software, the software in the cloud. It's just too expensive to do it. They're supposed to be things, and they're chatty. They need control. They need to make decisions continuously. And so we need to put, if you will, the data center that's otherwise in a cloud and the software, artificial intelligence software, in the car itself. And so, for example, autonomous driving cars, autonomous driving tractors, autonomous driving, box movers and manufacturing arms, and so on and so forth, and agriculture, farming equipment, and buoys out in the ocean, air quality measurement systems all over the world. Whatever it is, these things are so chatty. You really want to find a way to put the computer closer to the edge, or sometimes, and oftentimes, the data has sovereignty issues or privacy issues, or it's impossible to move it to the cloud for whatever reason. And so I think that AI is going to activate those things.
I was reading recently there are 7.7 billion humans on the internet, but there are 8 billion things on the internet already,
Yeah,
even before what you've been talking about, bringing AI in for edge computing.
that's right. That's right. I think the internet is going to be thousands of times bigger than it is today. The amount of traffic that's going to go through it is going to be just phenomenal. Now, some of the things that I'm particularly interested in, and beyond that, in the field of computer vision and computer graphics, is to move beyond transmission of video as the way of being together. Of course, today we transmit video, which is a two-dimensional image, but in the future we'll probably transmit perception, and from that information, I can reconstruct you in 3D. And so you and I could be in the same, basically, a greater sensation of being together. And so virtual presence is going to be possible. And so because of your invention, today we have the ability to share, to be in different places, but share one digital space. In the future, we'll teleport ourselves to different spaces. The teleporter is going to happen. It's just
So
going to
to
be moving photons, not atoms.
so to build all that and to trigger Metcalfe's law, as I'm fond of calling it, we're going to have standards carefully balanced, as you were saying earlier, balanced. They can't be too low level, they can't be too high level, and you don't need 0 of them. You don't need 1, maybe 2 or 3 will do, but 10 standards is too many, generally speaking. So there's this whole art of standards, and today we're celebrating a very successful trade-off in that decision, in that standards making, the Ethernet standard of 1980, which, by the way, bears no relationship to the Ethernet standard of 2020. There's been a lot of evolution over the 50 years.
Well, amazing work is built on top of your incredible invention. And so Bob, on behalf of all of the engineers and computer scientists in the world that participate in this industry, Metcalfe's law, this power law, this quadratic, has made it possible for us to enjoy an industry far greater than any of us could have possibly imagined in the early 90s. And I thank you for that, and for all of the people who are watching. They surely learned a great deal from all of your body of work and your teachings and your previous online videos. And I enjoy watching them, frankly. Your humor is incredible. And I want to thank you for the time you spent with me today. And I hope I'll have the pleasure of interviewing you some more in the future, and to tease out the body of knowledge that's trapped in there for everybody else to enjoy.
Thank you very much.
The contribution you made to computer science, as I mentioned, the technology is one thing. The wisdom about the standards, another thing. The specification of that standard. The thing that there's a phrase in our company: as much as needed, as little as possible. That is the specification that I put on almost everything. As much as needed, as little as possible. And the reason for that, in almost everything, I mean, I could find almost no application where that's not true. It could be seasoning of steak, as much as necessary, as little as possible. Everything that I find is people tend to do too much because they're so clever. They want to contribute more. They want to control more. Whatever it is, more. It is the genius that keeps it just enough. It is Steve Jobs' genius to not add that last stroke. It's
Right.
Picasso's genius not to add that last stroke. And that genius requires discipline and vision and self-control and wisdom and just all of that bottled up together. And Ethernet did that, and you should be proud of that.
One of the slogans, like your slogan just then, that we had during the Ethernet standardization process, the slogan was, anything that is not prohibited is mandatory. And the idea there is that standards in the past have been destroyed by options. Some branch of the standard could use this option, others. But in the Ethernet world, anything that was not prohibited was mandatory.
That's right. Therefore, it's essential.
Essential.
Yeah, as minimum as possible, as little as possible. Everything on that list, therefore, is essential. Yeah, it's really
The guys at
fantastic.
Intel wanted the Ethernet to have a 16-bit hardware address, but we wanted a 48-bit address. So the IEEE standardized both,
Aha.
16, and we had to build chips that could do both. But no one in the history of Ethernet has ever sent a packet with a 16-bit address. It just
Well, I guess if you
fell by
wanted
the
to hook up a
wayside.
few peripherals, if you wanted to hook up a few peripherals in an office, that might be okay.
Never
Yeah,
happened.
yeah. Incredible journey, and I am genuinely excited about the next step. One of the things, gosh, I wanted to talk to you about that, and it was something that I bet you wouldn't have you and I wouldn't have conceived of or even realized anyone would crazy enough do in computer science. So I would have never thought this was going to happen. So we knew that a computer is something that runs applications, and that computer was going to get faster and faster, and we're going to run bigger and bigger applications, and sometimes the application would be so large that you would connect a whole bunch of computers to run that application, and that application, of course, at some point became a fairly complex application, and it runs in a virtualized environment, what is known as the data center. And this data center was used by enterprise, and then one day it moved out into the cloud. They were smart enough to build very large data centers that run consumer services using off-the-shelf but fully integrated servers. They call them hyper-converged infrastructures, otherwise became the word hyperscale. And so the applications, one application would run in a server, and millions of people could be taken care of in the cloud. And at some point, the applications became so different. Some of the applications are very, very complex. Some of the applications are really just file retrieval. Some of the applications started to integrate artificial intelligence and speech recognition and image recognition and things like that. And so the emergence of this new way of doing application composing, which is called microservices, and the microservices are very, 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 very efficient and just the bare minimum system resources to create a container, a virtualized container, and this container could be run anywhere in the data center. This container will find the computers it could run in the data center. And that second part that I said is really important, because the data center at this point is no longer homogeneous. Some of it's got CPUs, some of it's a storage server, some of it is a GPU accelerated server. And you have an application with modules that are composed, and these modules are microservices that are running in different parts of the data center. I never thought, so that led me to the question, I never thought that Ethernet is the connection between macros or modules within an application. That is pretty amazing. Today's data center, Bob, is composed, these composable servers, what is called composable disaggregated infrastructure. And these microservices are orchestrated using this framework called Kubernetes. And you could scale up and scale down, and the data center is fully utilized. And the shock absorber, the system that's making it possible, is the Ethernet switch, the Ethernet network. And it's putting enormous pressure on the networking. It's now called east-west traffic, as you know very well.
Now, is this why you bought Mellanox?
It is exactly the reason why I bought Mellanox. It is exactly the reason why I bought Mellanox. It's always good to think about how to build your hardware by understanding software. It's, understanding software and understanding the direction of software inspires you about what's the best way to design hardware and evolve hardware. And if you look at an application today, it used to be largely microprocessors and interactions with memory. Then it became microprocessors and GPUs and interaction with memory. And now it's one computing node and interactions with another computing node with the Ethernet network in between. That now becomes the critical path of a data center. If we could make the latency low, both by making the latency lower and by making the bandwidth higher, the throughput of data centers, the energy consumed in a data center, the efficiency of a data center, cost of a data center, as you and I were talking about earlier, that customers really in the funnel analysis want more for less. The cost of a data center would drop dramatically. And so we saw this coming, and it's absolutely true. The east-west traffic in data centers is off the charts, and it's going to keep on going off the charts.
Would you consider, or are you considering Ethernet on chip?
Ethernet on chip, it will probably be not necessary, and the reason for not necessary because the protocols between our processors are very simple. Yeah, they're very, very simple, and we want to keep it as simple as possible, and everything that one processor sends to another processor is very well known, and so we could make a lot of assumptions about the sender and the receiver, and so that the protocol doesn't have to be nearly as sophisticated. But inside racks, it's basically networking, and in the future, Bob, we're going to have an application that partly runs in a data center, partly runs in another data center at the edge, for example, and then partly that application is running on an autonomous machine roaming around the world. And so that this way of composing applications connected by networking is fairly essential going forward.
That's a grand vision.
Yeah, so, it's pretty exciting.
NVIDIA, Mellanox, ARM.
We might be able to make something of this.
Yes.
Bob, it's such a pleasure. It's such a great pleasure and such a great honor.